Welcome PCS members and friends to our today's Tuesday IBS PCS seminar. It is a great pleasure today to have with us Professor Johannes Knolle from Technical University Munich. And I would like to invite our scientific host, Dario, to introduce our speaker. Please, Dario.
Yeah, thank you, Tilen. It's a great pleasure to have Johannes today for our Tuesday talk. So as usual, let me introduce our speaker. So Johannes got his PhD in 2014 at the Max Planck Institute for the Physics of Complex Systems that we know very well because our director Sergey was there probably at the time. So maybe they at a certain moment they crossed. After his PhD, he then became a postdoctoral fellow at the University of Cambridge, and later he joined Imperial College as a lecturer in 2017. And then, starting from 2019, he's now an associate professor. He is now an associate professor in Munich. Yes. Now, I mean, the scientific interests of Johannes are rather broad, and he works generically in condensed matter system, and more specifically, his research is focused on, let's say, unconventional phases of matter. And today, he's gonna give a talk about prethermal phases of matter. So, Johannes, I think you can start now.
Yes. Okay. Thank you very much for this kind introduction, and also for this nice invitation. Yeah, it's a pleasure to be here virtually. And yes, as you see today, we'll talk about prethermal phases of matter. And since I think it's a rather heterogeneous audience, I will also spend some time to introduce what we mean by prethermal here. Also, just for the talk, if there are any questions, please just unmute yourself, shout in, and so yeah, we can also keep that quite informal. So if you have a question or want something to be clarified and so on, yeah, just please ask. Let me start very broad to tell you what we are interested in here, and we are basically trying to address a very old question, and this is the question that has been with us for many hundreds, not thousands of years, namely, what is the nature of matter? So if you here see, for example, this geyser in Iceland, you see that water can be in many different forms. It can be in ice or in vapor or liquid. And the first person who really contributed to our, let's say, modern understanding was probably Democritus, who conjectured already that all these different forms just come about because we have a huge collection of very simple entities, and they just have different forms and arrange themselves in different arrangements, and we just have a huge number of those, and then different arrangements would give to all these different kind of phases. And this idea of atomism is, of course, still very much with us today. And here I also show you this beautiful picture of a crystal, and this again is this regular arrangement, which we still understand today, and we'll go more into this. So then, a part of understanding phases that we see around us that nature gives us, there's also this idea of creating new phases in the laboratory. So phases that have desirable properties. And here I just show you this picture of the alchemists of the Middle Ages, whose effort, of course, of turning things like sulfur into gold weren't successful. But as we all as scientists, and especially the experimentalists maybe among you know, is that sometimes you want to do one thing and you stumble about something else. And so this idea that we can create new phases in the laboratory, or first theoretically try to propose new phases, this is also something that we'll come later about in this talk. But normally I'm interested in more exotic things like proper quantum phases, correlated quantum phases, and here I've shown you this picture, for example, of the fractional quantum Hall effect, and I will come back in how much we need strong quantum correlations for realizing some of these sought after phases also in the second part of this talk. So our canonical understanding of phases of matter, let me also remind you of that. This is that we now understand that almost all phases that we see around us can be essentially described by the Landau paradigm, where we can look at the symmetries that the equations of motions, for example, something like the Schrödinger equation or the microscopic description, the symmetries that these obey. So here, my simple example would be, think of a gas of atoms that interact with each other at high temperatures. They would be all random in space, and it wouldn't actually matter where you are in space. The interactions are always the same, or if you look around yourself, everything looks random, and that means there is what's called a translational symmetry in the system. And only if you cool the system, then all of a sudden we very well know that we will break this translational symmetry, this continuous translational symmetry, by forming a crystal lattice. And here, let's forget about the colors for a moment. You see that now you have this very regular arrangement of a crystal lattice, and now, of course, the world looks different whether you sit on a lattice sides and look around you, or whether you sit on a pond in between. And that's what we mean that symmetries are broken. And the symmetry breaking is described by order parameters, and that's our canonical understanding. Now here we can have continuous space translation symmetries that gives us space crystals, or you can also then, once you have a crystal formed, the electrons that might propagate on these crystal lattice sites might also interact and further break down this discrete lattice symmetry further down, for example, what's called a charge density wave formation, where the electrons, for example, want to sit predominantly on the blue lattice sites and not on the green one. So you can further break down a discrete translational symmetry. There are many other forms that you very well are aware of, for example, spin rotational symmetry to give magnetic states and so on. And that's really our canonical understanding. And here, the important bit for this talk is that you understand that the phases that we get have a lower symmetry than the underlying equations that govern the system. And that's what we, of course, know as spontaneous symmetry breaking. Now, so this is the first canonical bit, which we then want to generalize. The second bit is to understand equilibrium phase of matter, is how we actually go to equilibrium. And so this idea about thermalization or equilibration here is motivated by the simple observation that if you have a highly out of equilibrium situation, so for example, here this glass of water with ice and lots of kinetic energy, we actually know that if we just wait long enough, it essentially will equilibrate, meaning that we know that all macroscopic systems, or generic ones, they will reach some steady state. And we know that this is a very old problem, and we classically need, the agodicity hypothesis and classical many-body chaos in order to see thermalization. But the key thing is really that if we have an equilibrium phase, then it can be described by only very few macroscopic observables. So that is, of course, why we can then use things like the central limit theorem and so on. And then in the end, instead of keeping track of many degrees of freedom, we just have a few macroscopic observables. So the key questions for this talk is here, how and when do we reach thermal equilibrium? And in particular, since we're interested in phases of matter, the question is, are there novel non-equilibrium many-body phases on the way on this path towards equilibrium? Good. So then here's my one slide introduction into thermalization in a quantum many-body system, because we'll need that later on. And the first basic observation is that if you have the full many-body wave function of a macroscopic quantum system and you time evolve it, since it's a linear equation, it will never actually thermalize or equilibrate in a strict sense. But in the 90s, people then asked the question how we can nevertheless think of thermalization. And the idea is really that there is no global thermalization, but nevertheless, if you just look at local properties, then the rest of the system, you can think pictorial acts as a bath, and if you locally just measure the system, it's looked as if it's thermal. And here, this is the standard picture for that. If you now measure some local operator, local correlation function in eigenstates of a generic non-integrable many-body system, then you will see here that it becomes a smooth function of energy. So knowing the energy of an eigenstate will correlate strictly with what a local observable will do. And actually here, the spread here is just finite size effects, and there are very strict ways to predict how this actually will become a sharp curve in the thermodynamic limit. Now, in the last decades or so, or 2 decades, it was very much of interest to understand how we can invade this generic behavior of thermalization. And the key advance was the idea that built on the seminal work by Anderson, namely that if we have localized states in the presence of spatial disorder, then this can even be robust in the presence of interaction. And now what one realizes is a new phase of a many-body localized phase, which is characterized, for example, by the failure of this eigenstate thermalization hypothesis. So in contrast to this picture here, if you measure eigenstate, like local observables and eigenstates in an MBL phase, you get, basically answer all over the place. So it's not useful to actually know the energy of the system. So in that sense, thermalization also doesn't really help you, or doesn't make sense. So this is now, having set the stage for a few things that will go into the new things that I will discuss. Here's my outline. So after a brief intro of equilibration, phase of matter, and how that can fail, I want to first tell you about prethermalization, and it will concentrate on what's called Floquet system, namely periodically driven system, and what prethermalization means in that context, and then introduce a few prethermal phases of matter. So the first ones that we also worked on are higher order and even fractional time crystals. And then this will all be based on quantum physics. And then just very recently, we asked the question, how much quantum physics do we actually need? Can that also be realized in classical setting? And the short answer is yes, and that will be the part on classical prethermal phases of matter. And so the last point is really optional, depending on the time, that you can ask beyond periodically driven system, can we also in aperiodically driven system have new prethermal phases of matter? And the answer is yes. And if I have time, I will show you a few examples of this. Good. Okay, so that's the outline for the talk. So let's start with periodic driving. So by periodic driving, I mean that we have discrete time translational symmetry, meaning think of a Hamiltonian describing some quantum many-body system, and it just comes back to itself after each period capital T. And so we know that then energy is conserved modulo its frequencies to 2 pi over T. However, we also know that if you take a generic non-dissipative many-body system and you drive it, you shake it, so then you will heat it up. So energy is not conserved. And what that means, so here, think of shining a laser on something, driving it periodically. So that means if you heat it up, it will absorb so much energy until we reach what's called the trivial infinite temperature state, which has only trivial correlation. So really think that everything just goes towards the trace of whatever operator you want to measure. So now a big question is, if you want to do something interesting with periodic driving, you have to prevent this heat death to infinite temperature. And one of the ways to do that is, again, to take many-body localization. And it turns out that many-body localization, if you take an MBL system and drive it periodically, weekly, then you can actually prevent the energy absorption completely, meaning that up to infinite long times, the system can still remain stable without actually heating up to a trivial state. Now, that has its drawbacks, and we'll come back to that. The interesting other bit, how you can not prevent heating up, but actually delay it to very long times, is by just driving it quickly. And this was worked out theoretically in a number of works here, for example, by Abanen or Takashi Mori et al. In these works. And I want to tell you a little bit more about how this comes about, because that will be also the key ingredient for using that for building new phases of matter. So this goes under the name of prethermalization. And here the idea is that if we have a Floquet system, instead of looking at the time evolution operator for an entire long time, you can just think about time evolution operator over a single period. And so that then can define, just via this equation, a Floquet Hamiltonian HF. And now the idea is that then calculating time evolution of a wave function at late times is just simply just have to apply it. This Floquet time evolution operator n times, and that gives you the stroboscopic time evolution. Now, mathematically, what you can do is you can now take this Floquet operator, and there's a formal way of writing this down as an expansion in the inverse frequency. So meaning that if the frequency is large, you get some small parameter, And it turns out if you want to time evolve up to a given time, you can actually truncate the series, and that will give you an effective Hamiltonian that describes the time evolution until that effective time. And so the upshot of the Horn analysis is that there is now a time scale in the system which is exponential in the frequency, times some constant set by the local energy scales. And now you have a system that is described by an effective, if you want, time-independent Hamiltonian in this long pre-thermal regime. Okay, and what that means, we'll show you in a second. So that's the formal way, on this inverse frequency expansion. There is a very simple, intuitive way that lets you understand why that happens in the first place. So this is just basically a mismatch argument of energy scales. So you can think of some simple spin chain, and I'll show you examples of that. And there is, basically local processes. Think of local spin flip processes, which come with some local energy cost, which we call J effective. Now, if you drive the system with a frequency omega, the system can only absorb energies in chunks of omega. So if you drive it very fast, that omega is very large, you need many, many local processes to even absorb one quantum of this energy omega. And that's extremely unlikely. And this is why the system, will shake a little bit, but will actually not efficiently absorb energy. And that's the reason why, in the end, if you drive slowly, it heats fast because the frequency matches the local excitation energy. And then you get a quick buildup of the entanglement entropy, for example, or think of some other measure here. If you're now on the fast driving regime, you have this big mismatch. And then what happens is that the system just equilibrates to some pre-thermal state. And this pre-thermal state, that's the amazing bit, is described by an effective pre-thermal ensemble over an exponentially long time. So if you want, you can tune that astronomically long by just making the frequency long. And so this regime here is different from MBL, that eventually it will still heat up to infinite temperature, but nevertheless, it gives us an exponentially long time scale. Right. So this is, of course, the underpinning of this huge field of Floquet engineering. So the idea that you can now take a Hamiltonian, drive it periodically, and then engineer.
Johannes?
Yes.
I have a question, but maybe it's just naive. So can you go back?
Yes, please.
Suppose that somebody arrives with an Hamiltonian and doesn't tell you, because you told us that essentially you are doing an evolution which is effectively controlled by an effective time-independent Hamiltonian.
Yes.
So is there a way to distinguish that this Hamiltonian is a prethermal Hamiltonian and is not an MBL Hamiltonian? Or maybe, if you arrive with an Hamiltonian, if somebody arrives with an Hamiltonian and doesn't tell you that this is coming from a Floquet operator and so on, is it a way to distinguish an MBL Hamiltonian from a prethermal thing?
Yes and no. So that that depends a little bit on, if you're in the really high frequency limit, and basically the lowest order frequency, inverse frequency expansion is already a good way, then you will not be able to tell, because the effective Hamiltonian will also be, more or less local and will just look like any good Hamiltonian. If your frequency is not in the really high frequency limit, and you have many, many terms that go into this effective Hamiltonian in your high frequency expansion, then what will happen is, because you have an underlying Floquet system, the system will actually also have non-local contributions, which will not look like, some generic system.
I see. Okay.
Yeah, but probably whenever it's useful to do that, you will probably have a hard time telling the difference.
We have also a question from Alexei.
Sure.
Yeah, thanks. One question related to Floquet and heating to infinite temperature. In principle, you can stabilize that by coupling a system to a reservoir. What would be the catch?
Yes. So I think that's a very good point, very valid point. So this is the other way of having a dissipative system. But in the entire talk today, I basically want to concentrate on non-dissipative systems, and then basically ask questions about, what can we basically have for systems which are not coupled to environment. Yeah, but I mean that's obviously true.
Well, no, that I understand. I think, yeah, thanks for. So I think I should really make my question more specific. So essentially, what is bad about? I mean, why looking specifically at non-dissipative systems?
Why looking specifically at non-dissipative systems? Yeah, I mean, good point. I mean, we could also ask, look at dissipative systems, and there is, of course, a whole rich structure. So one of the answers, which, well, maybe we come back later, of is, in some sense of how much quantum mechanics you need, or how much, how non-trivial some of these effects then that we're looking at, and then you can ask for the fine details of what's the difference between a like a dissipative system and a non-dissipative system. Yeah. So I don't want to go too much into this into these debates of maybe we can come back to the question when we discuss my brief introduction to time crystals, because there I think it's a big question, whether you want to really have a dissipative or non-dissipative system. But in principle, yes, fair enough. If you have interesting physics for a dissipative system, sure. I mean, I don't see a reason why I should exclude them.
Okay, yeah, and I have a second quick question that's actually related to the ETH slide. No need to go there. So my understanding is that if you look at the system that's ergodic where ETH holds, then any local operator would see after some time, you would see equilibration. So now, is there an understanding how local the local operator needs to be? So if you start looking at various crocodiles, making them larger and larger, what is the length scale, perhaps, an appropriately defined length scale that defines when you stop being local? Because I guess if you take a system that thermalizes, but you take an operator that's basically spans the entire system, or essentially as non-local as it could be, you would see you're not thermal. So my question is, what's the scale, sorry, not the time scale, the length scale that defines when you go from one to the other?
Yes, no, that's a very good question. So yes, so if you, for example, measure the entanglement entropy and things like that, something really non-local, then of course you see that you're not thermal. So intuitively you should think of a length scale which is short enough that you still have an extensive number of degrees of freedom that can act as a path around it. Okay. So in that sense, I think whatever patch you locally look at, it's basically, its density basically should go to zero, I would say. So that is that I think should be the obvious way. Yeah. So you want really that you still have a macroscopic path of the surrounding system. So whenever you measure a correlation that picks up, a finite fraction of the total system, then I think you would see actually that it's not obeying ETH.
But is it really universal, or it might depend on the system, with some systems being simpler to construct, is some being harder?
Well, okay, yes. So yes, it is. But this is now going into fine details about ETH, because you of course can have more structure. There's things like weak ETH and strong ETH, basically asking whether all the eigenstates of the Hamiltonian will obey ETH, or whether you might have some outliers of measure zero, and they could then be athermal. And so this is this whole idea of quantum many-body scales and so on. So you can have much more structure, it can be more infinite. But I think for this talk, mostly we think of generic systems which don't have any pathological extra bits.
Okay, thanks.
Yeah.
Can I ask?
Johannes, if I may just add another question on that. So how can I tell, by just observing the dynamics of the system, whether it is a Floquet-driven system or, let's say, truly dissipative system, as we kind of discussed right now? So what is the difference, so to say?
Oh, what's the difference?
Conserved, and so what do I have to, what do I have to check?
Well, so locally it might be extremely difficult to do that, or probably maybe also impossible, but of course globally, so that information and everything is conserved in a non-dissipative system, So basically, if you trace the entanglement entropy, you will see things like this, that this is just conserved. So locally, you're right. It might be extremely hard to tell the difference.
I was always wondering what the difference between a driven and a dissipated system are, or is, what the differences are. Anyway,
so
maybe
again, I think it's a valid point, and I think I mean, if you want to do something new and interesting, so you somehow need to get rid of this heating effect, and dissipation is one thing. I think why I'm a little bit hesitant of diving head on into just allowing dissipation is just that there's a huge discussion out there about some prethermal phases, whether they are trivial or whether I should basically think of anything to be a time crystal or not. And I just deliberately want to avoid the discussion because I'm not sure how productive that is.
Okay, thank you.
Short question. So there's a long time life scale that's exponential. Am I right that this is coming from the short-range interaction? Like
yes.
If I have all-to-all coupling, I don't see this Prethermalization. Am I right?
So yes, so you have to be careful. So generically, you probably wouldn't, but in practice, it depends a little bit also on how you drive and how you couple it. So you will see later on, we will study long-range interaction, power law interacting systems, and they will still show that. And we will even see one system where we have an all-to-all coupling, and so that comes in a few slides.
And you still have this exponential.
Yeah.
Oh, and
no. In that case, it's like if you're on the strict all-to-all coupling limit, the way we drive it, the system will actually forever. So we don't have this exponential scale anymore. It doesn't heat at all. Yeah.
I see. So because am I right that the exponential comes from the fact that like when one flips, other have to flip simultaneously, so that's exponentially difficult to.
Precisely, yeah. So you still want this energy scale that governs the excitations to be something local. Yeah.
I see. And your example is probably different mechanism.
Yes, yeah.
Okay. Thank you.
Okay, good. So then let me here come back to Floquet engineering. So, you have seen all these beautiful works to, for example, induce topological insulator states in graphene by the first proposal by Takashi Oka and Naoki. And now also in cold atoms, this idea of engineering, for example, artificial pilot phases to get topological system. This all is basically building on prethermalization, because that means you have this long time scale where you can think of engineering some effective Hamiltonian. So let me pick up one aspect of this question, because one thing that we did 2 years ago was to ask, like, can we also realize via periodic driving a Hamiltonian that violates ETH? And the answer is yes. And so one thing that we did in this work is that we essentially took a Hubbard model-like system, drive it periodically, and then engineer kinetic constraint, meaning that now, whether you can hop from side to side depends on the occupation on the sides, and you get what's called Hilbert space fragmentation. I don't want to go into detail of that, but just here to highlight this, that if you, for example, then measure some local observables in now Floquet eigenstates, then as a function of the frequency, you can basically see ETH-like violating behavior. Now also, that's the weird bit, on a prethermal time scale, where it's basically for high frequency, for very low frequency, the system obeys something like a ETH, and it's like a smooth curve as a function of the Floquet energies, and then just you can crank up the frequency, and then you see basically that your Hilbert space connects into all disconnected sectors and is not generic. So just to highlight this, so Floquet engineering can be used and is really a powerful tool for looking at many new types of physics, which just you might not have realized like for a static Hamiltonian. And so that gives you a way of doing that. Now, but we want to ask the other question, namely not of realizing a system that also has a static counterpart, but you want to ask, whether there are also Floquet phases that don't have an equilibrium counterpart. So I told you all these broken symmetries, continuous space, breaking the continuous space translational symmetry gives you a space crystal and so on. But you can ask the question, can we also break time translational symmetry? And that will then, be a phase that doesn't have, by definition, no equilibrium counterpart. So this first idea of breaking continuous time translational symmetry was put forward by Frank Wilczek and then quickly disproven that it's not possible. So there are various no-go theorems, essentially, energy conservation arguments. But then it was realized that if we have a Floquet system, we have a discrete time translational symmetry. The system repeats itself after a lattice in time set by the lattice constant capital T of the period. And so then it was realized that we can take this discrete time translation symmetry and break it down and then get what's called discrete time crystals. And this has been, of course, of big interest. And since we will generalize these concepts, I want to introduce that in a second. And there is a very simple soluble limit that almost makes it trivial. And again, we are thinking about non-dissipative systems and just having time evolutions of a Floquet system that repeats itself always. So over one period, we just have time evolution with some, let's say, short-ranged Ising Hamiltonian. And you can think of the system having disordered couplings, and then some operator X, which just is a global flip and flips all the spins by 180 degrees. And so then if you look at the time evolution, so not much happens. So there's like dephasing in between if you start with some simple product state in the Z direction. And then you see that if you apply this Hamiltonian, which is now periodic with capital T, if you apply that twice, you come back to yourself, the system comes back to itself. And you also see that if you square this Hamiltonian, so then, flipping something back and forth, about 180 degrees is just the identity. So you see that there's an effective Hamiltonian describing the system every 2 periods. And this is just a simple Ising Hamiltonian. And now if you measure any observable, you will see that your system is time periodic with period capital T, but some local observable, like, some local Z polarization comes back to itself every 2 periods. Yes.
X does not commute with the Ising Hamiltonian. So the square, don't you have to worry about the commuting of X and H Ising?
Yes, but here for that system, it actually does commute with it. It's just 180 degree. It's just 180 degree flip.
Okay.
Yeah. So on that level, it almost looks, like you haven't done much and it's trivial. But the whole point is that it's a many-body system, and now you have to ask about stability. Okay. And so the point is that if you would now have imperfect flips, where you then have to really worry much more microscopically, then you just do the time evolution, and then you do a Fourier transform, and then you see for imperfect flips, so flipping 180 degree plus epsilon, now the frequency will split into 2 peaks, and it's not rigidly locked. But now if you switch on many-body interaction, meaning having proper Ising interactions that give you rigidity, so even for imperfect flips, the system self-stabilizes and will be locked at this frequency 1/2 here. And the point is that if you have disorder in the system using the stability of MBL, this will persist forever. And this is why people also want to think about non-dissipative system, because this is really a phase in the stricted sense that it's stable, that it has some well-defined long time infinite system limit, and that's partially why there is so much interest in this. And again, there's now many experiments. There are loads of discussions of what is like a genuine quantum time crystal, whether it's, what is a dissipative system. And in some sense, I said, don't really want to go into this discussion, because any experiment that you can ever do will always be either, for a finite time scale, which will make it hard to really see whether it's prethermal or absolutely stable. And, you will also have, some small dissipative terms. So I don't really want to go in this direction, but rather what I want to do is I want to ask, like, can we do something without MBL? Can we also have time crystal-like behavior in prethermal systems without need for disorder? And the answer that you will see is yes. And there's actually a whole new world of time crystals or of non-equilibrium phases out there that go way beyond the simple period doubling things that you can get with MPL. So first, if you just use prethermalization, so again, fast driving, so then the only price you now pay is that this doesn't persist forever, but it has actually this long time scale. And we also know that we can now think of a prethermal Hamiltonian describing that system. And if you want to do a proper quantum simulation of a quantum many-body system, then you realize you run into a little problem, namely that you want that this phase here is now described by some effective Hamiltonian, and you know that a time crystal is basically one which is an ordered state every two period. But we know that in one dimension, we can't have, an ordered easing state. So what that means in one dimension, if you want to do proper quantum simulation, you need to go to long-range interactions, power law interactions. Which is, of course, very well known how to get an easing transition for a one-dimensional system. And indeed, you can also ask again the question about stability, and the idea is very much the same. So it's a stable phase of matter. The only price that you pay is that it's not infinitely long stable, but only exponentially long in the frequency. So one thing that you can also ask, like, how do you detect the time crystals? So here, that's the spin flip strength. Think of basically flipping 180 degrees plus epsilon, and then you just basically look at the Fourier transform. And if you have a trivial system, it will not be stable, but if you have interactions, it will actually form a stable plateau. And this is the signature of rigidity. And we'll use that in a second when we generalize that. So the big question that we asked ourselves when we came to the field 2 years ago was, is this simple period doubling 2DTC really the only phenomenology that you can get, or is there something more interesting than just period doubling there? And this is this new chapter here on higher order, and you will see even fractional time crystals. And what we will do is now we will take a one-dimensional spin chain. The ingredient is that we have some power law long-range interactions, which we need because we're in one dimension. Then we have some competing local energy scale just as a tuning parameter. And then instead of basically having this discrete flips, we actually take, the square pulse of flipping, we just replace it by this 1 plus sine term. And it turns out that we don't need discrete flipping. The system with interaction stabilizes itself, that you can also do this continuous variation of the sigma x interaction. So here now, this is the frequency of some local observable. Fourier transform that as a function of flip strength. So again, here at 1/2, we get actually a line. It's hard to see this actual data. And that's the 2DTC. And now you just scan this field here, and you now find something really surprising. And the point is that we not only find a 2DTC, but we find also, a period quadrupling. And then the interesting bit is you find even these fractional numbers here. So if you zoom in, then you see something where you have an entire zoo. So you have a huge, rich phase diagram, which are all non-dissipative, non-equilibrium phases, which all persist up to an exponentially long time. And then the question is, of course, how do you understand that? So this is something maybe to stress here. You would never get that in an MBL system, because there you can't actually have these higher order DTCs because of the disorder in the system that is really necessary. This would always basically destroy that. So let's look a little bit more into this in detail. So here, the way we do that, we can now do a simulation where we plot like the value of the local spin SZ as a function of SZ component at the azimuthal angle. And then here we can now do that as stroboscopic times. And that gives us, of course, these Poincaré maps here. And so here you see what you would get from this analysis for a 4DTC. So meaning that we will have that in one period, basically we flip 4 times the spin before it comes back to itself. And then you can directly see also what the spin is doing. It just jumps from this islands of stability, 0, 1, 2, 3, and that always repeats itself. And that gives us also now a way of understanding higher order DTCs, for example, this 8DTC, where you just now jump around in 8 steps, and even these fractional DTCs. So for example, this would be 8/3 DTC that you've seen in the phase diagram before, where you now not jump around consecutively, but you go from 1 to 2 to 3 and so on after you come back every 8 times to the same state before. So this is now reminiscent, of course, of something like the devil's staircase that you've seen in dynamical systems theory. But here, this is a non-distributive quantum many-body system. And let me also stress that in order to do these calculations to very long times and so on, we have actually so far worked in a limit that is treatable. Namely, we have, let me go back to the Hamiltonian, we have worked in a limit where we have used all-to-all couplings, where we can actually map the system onto a special model and then also use things like the translated Wigner approximation to study the system. But you now want to ask the question, is that really something that is is just special to the all-to-all coupling? So then comes the hard bit, because now you want to do that beyond a limit that you can treat, and that is also beyond the numerical capabilities. And so one thing that we then picked out is, for example, let's look at the 4DTC as an example. And then we developed a nonlinear spin wave theory, where you essentially go into a rotating frame and then count the number of excitations that would disorder your prethermal state, your 4DTC, and then look at the number of excitations that would be detrimental as a function of time. And that allows you also to pick up an entire phase diagram, where now this is alpha, which is the exponent of the power law interactions. And then here, this is the Fourier transform looking at the order parameter of the 4DTC. And you see that indeed, we find that also for not all-to-all coupling, this is a proper stable phase. And there's, lots of indications that this is a true many-body phase that we find here. And we would assume that this goes hand in hand for all the other phases that we find.
Sorry, maybe I missed that. What's the difference between the ones that have been studied? I mean, the models that have been studied and this model?
Oh, yes. So previously, what people have done is basically mostly MBL physics. Okay.
Okay.
And then it's really just what I said, some Ising Hamiltonian flip, and you just get period doubling. There was some work on quantum prethermal DTCs, but the only thing they did is basically 2 DTCs.
And why did they miss the devil's staircase physics?
That's a very good question. I don't know.
Okay. Oh, so you think that should be there in their models too?
That should be there in their models. There is a caveat there. The caveat is the following. So if you look at our phase diagram, where do we see a 4DTC, and you just do simple exact diagonalization, which 99% of the researchers do in that field, because you want to do time evolution of a many-body system, then you don't see it, because the 4DTC, I mean, I might have a slide in the end, maybe in the discussion I can show you. The 4DTC only emerges really as a stable plateau, for 50 sites or even 100 sites. Okay, so it's extremely hard to see an exact diagonalization. So that's why we first went to the all-to-all limit where we could treat it, and then basically we developed around that all-to-all limit then semi-classical approximations to see it. But the answer is really they have missed it for a good reason. Because I think it's very hard to see actually in ED. Maybe if one is brave enough and does something like DMRG time dependent or tensor network, you might see it.
Also, I think I missed why the NBL Floquet physics cannot have this double staircase physics.
Yes. Okay. So the simple reason is basically think of what the disorder does. So the simplest case is you just take the Ising Hamiltonian and add a disordered field to it. Yeah. So, but now if you always rotate your spin by 180 degrees, it basically doesn't do anything. It doesn't give you any dynamics. But as soon as you would, for example, want the 4DTC and you rotate it in the plane, then having a disordered field will basically rotate all the spins locally, completely in different directions. And then you would very quickly basically just scramble everything and you wouldn't have any rigidity. So that's really, any disordered in the field kills anything of that.
I see.
Yeah.
Okay, I see. Thank you.
Yeah. Good. Let me see. Yeah, because time is, so then, yeah, good. Good. So then let me continue, because so far, you saw that one of the big problems in the field is that how to actually treat that. Yeah? Because I told you exact normalization is really difficult to do, and you really miss a lot of nice and new physics, like, you know, this old devil's staircase, whole big non-equilibrium phase diagram. And so one question you might ask is, you know, what is really quantum in these systems? Namely, if you think of thermalization, you can just also classically think of thermalization as that you want that the expectation values of local observables only depend on things like, you know, the energy that allow you to define temperature. And in particular, if you compare now classical and quantum theory, you just see that the underlying mechanism of thermalization is very different. Namely, you need chaos and ergodicity classically, and you have things like the ETH, and also, you know, the features are different. However, the intuition of physical processes, namely a mismatch between some local energy, some local processes which thermalize the system, and the mismatch between the energy of the drive, that is of course very similar. And just a few years ago, which was funnily enough a few years after people have thought about prethermalization in quantum systems, which I think is due to the fact that it's a formalism thing, that, you know, the inverse frequency expansion, the Floquet Hamiltonian, is very natural in a quantum system and not natural in a classical system. But these two papers here by Takashi Mori and also Polkovnikov, who I saw will also give a talk later this week. So they actually pointed out that you can get prethermalization also in the classical system. And so then we set out to understand whether we can leverage that prethermalization also to get prethermal phases in classical systems. In particular, we want to look at systems which, you know, you can't treat quantum mechanically. For example, then 2D, 3D time-dependent interacting system. But let's first essentially take the same Hamiltonian as we did before, long-range interaction, and then we can now slightly change the model in the sense that we want to have stroboscopic time evolution, where we switch between these two, but this is really just for technical reasons. You could also do it with continuous time dynamics. And then we just take here these semi-classical equations of motions, these Landau-Lifshitz equations for the system. And you also know that you now have to think a little bit more about the initial condition. So we always will polarize the spins and then give it some small random directions, some small spread to basically put some energy in that there is some dynamics classically. And we also define some new observable, which will be very helpful classically, which is basically the distance between two copies, S and S prime here, which just differ by some small deviation in the initial conditions. So this is basically an indicator of quantum of classical many-body chaos. And then the first thing we wanted to do is basically just benchmark. So this is a bit of a busy slide, but the first upper half up here is basically the full quantum calculation of a 2D TC in a prethermal system, which has also, by the way, been implemented experimentally. And here, the lower part is the corresponding classical system for that. And you can just look, for example, here on the system at a low initial energy density, where you see this period doubling and this exponential scaling, because that's different frequencies. And we see exactly the same thing in the classical one. So the message of this slide is really that if I just show you the data, you wouldn't be able to distinguish what is quantum, what is classical. And that's somewhat surprising because, these people, they actually hadn't even thought that this would be possible classically. So people, had the presumption that, this is a genuine quantum thing. Of course, if you look at the entanglement entropy, this also has this interesting two-step behavior from prethermalization. And here, this we don't have classically, but we can look at our decorrelator, and it turns out that the decorrelator is the classical analogon of measuring information spreading, and it behaves essentially the same as the entanglement entropy in the quantum system. So the message is that we have now benchmarked this for 1D system, but of course now we have a system of classical equations, which we can study also in higher dimensions. And here, this is the first result of a two-dimensional system with short-range interactions. And now we want to look at a 4D TC. So here I show you now, this is a system of 200 times 200 spins. And now here is the color coding for the different directions of the spin components. And you see that, as we see for 4D TC, you come back the state itself after 4 periods, and we drive that quickly, and you can see that you have a few local excitations, but still you have this prethermal order which persists up to exponentially long times. And eventually here in our system, after 2 to the 5 periods, we see that we have these domain walls appearing, and then we heat to the thermal state at very late times. So now we basically see that we can have proper simulations in 2 dimensions, which would never be possible. And you see that, you know, the phenomenology persists also in this purely classical non-dissipative setting. And here just, you know, we can even do that for 3D. And this whole devil's staircase, which I showed you, also persists for these classical prethermal phases of matter. And that, you know, is of course one you know, completely open field where you can now think, of course, this idea of Floquet engineering or looking at non-equilibrium phase diagrams. That is something which is surprisingly simple and so far hasn't really been studied at all. So maybe some more details on the 4DTC, where we can now use this way of plotting systems first on a linear scale and then on a logarithmic scale. And here first on a log and again linear scale, where you see what happens actually is when you start driving the system, there is of course chaos spreading. So this is here by this exponential increase of this decorrelator. And then you settle into this prethermal regime where the system, now if you would measure local observables, they would look as if you would calculate them from a thermal ensemble. But if you would look at more global properties, you would actually realize that also classically the system is only in like a local crypto equilibrium, but not in a global equilibrium. And then eventually, if you wait long enough, it will still eat up to an infinite temperature state. And you can now, you know, map out these full non-equilibrium phase diagrams where you have these new prethermal phases appearing. Good. So the idea is, of course, that we have you know, the separation of time scales, and that really is the whole idea that you can then engineer phases that don't have any equilibrium counterpart as well here. Good. As I said, there are many open questions, and this is something which is I think still in its infancy. But you can, you know, of course, also ask questions now. What happens if you couple that system to a bath, or if you have dissipation in the system? So that might be another direction to go. So, you know, looking at the time, maybe I should skip this final part, which would be asking the questions whether you can also go beyond periodically driven system. And
Johannes,
yeah.
You can take 5 minutes still.
Yeah. Okay.
Is that
Good.
enough?
Yeah. Sure. Yeah. Let me fill that very briefly. So the question is basically, can you have prethermalization without time translational symmetry? Yeah. So anything that had been done was on periodically driven system, and we wanted to understand, is that really all there is? So it's you know, very basic questions. And of course, if you have a system that you drive with some random time dependence, it will just heat up. There's not much you can do except for driving extremely weakly. But we want to really also have a system that we can drive strongly, but still would show prethermalization. There is a simple generalization of the Floquet system if you drive it, for example, with 2 smooth frequencies, omega-1, omega-2, which, you know, would be their ratio would be irrational. But in some sense, that basically brings us back to the Floquet system, because we can actually think of a higher dimensional Floquet lattice. But the one thing that we wanted to look at is systems with stroboscopic time dependence, meaning that you have basically a continuous spectrum in frequency space. And there, intuitively, we have seen that if you drive slowly in the Floquet system, the low frequencies, these are the ones that kill you. These are the ones that heat you efficiently. So you somehow want stroboscopic time evolution, but you want to somehow kill the low frequency components. And you know, this spectral engineering can essentially be done, and it can be done in a very systematic way. So what we'll do here, I just show you the protocol, then maybe one slide, and that you get the gist of it. So we basically have 2 Hamiltonians, H pluses minus. For this property here, it doesn't matter what it is. Just think of any many-body system. And then we can define 2 translation operators, U plus U minus. And then you already see that we can now just pictorially think of some analogy of dipoles. We just, call the U plus, here with a plus charge, the U minus with a minus charge, and then a periodic Floquet system where it would just be a periodic arrangement of minus, plus, minus, plus, minus, plus. And we can then also calculate here the stroboscopic time evolution of, any wave function time evolved. But we can also draw randomly between the plus and minus dipoles. Okay, so now you see that this has no time translational symmetry because we randomly draw either from this right pointing or this left pointing dipole, but there's still some structure in there. The structure is you can never have 3 plus in a row, for example. And this now you can generalize not only from dipoles, but you can do it from quadrupoles. So you have 2 quadrupoles, and you can randomly now draw a time dependence from a sequence of random quadrupoles, and you can basically generalize that to arbitrary n. That gives you in this limit what's called the quasi-periodic 2 more sequence. And the upshot is that if you look into the mathematical proofs of why you should have prethermalization in a Floquet system, namely that you can bound the time, the evolution over one period and compare that to the evolution with the effective Hamiltonian over one period, which is just the average of the time-dependent Hamiltonian over the full period, then this is just bounded here by the inverse of the frequency squared. And this is the very same bound that also applies for our random multipolar driving. Because you see here, whether I write this as U plus or U minus, it doesn't matter for the lowest order frequency expansion. It's the same as the U minus U plus. And this you can generalize actually to all these multipoles. And the upshot is that, let me maybe show you some results. So then if you look at the energy density and you have such a random multipolar driving, you still get prethermalization. So meaning you have a long exponential regime before it dives down. Then the time scale that you want to extract, you can just operationally define that. And then you can plot that as a function of frequency. So this is the limit of 2 Morse driving, which looks still exponential. Turns out that it's actually slightly slower than exponential. But the interesting bit is if you have no time translation symmetry, if you have like a random, for example, dipolar drive, you can actually also see that you get new prethermal regimes, which now don't scale exponentially with the frequency, but they scale with the power law. But the main message is really that it's less robust. It doesn't scale exponentially, but it's a universal scaling. So depending on which multipole you drive it, so the multipole is given by this small number n, which is discrete number n equal to 1 for the dipole. So then this gives you a universal scaling of the prethermal lifetime, which is really independent of any microscopic details of the Hamiltonian. So that really works for any system, as long as your frequency or your inverse 1 over t is large enough. Good. So that's, I think, the upshot. One can relate that to some spectral properties, but I think we can build time crystals with that as well. So you can build a random time crystal without any time translation symmetry. But I think I want to go to the summary here. So I introduced some basic things of prethermalization in driven system and also time crystals and MBL systems. And then I will work on generalizing these to clean systems, where we have now uncovered a whole new zoo, which is has a much richer structure than just the simple period doubling DTCs. And you not only get higher period n tupling of non-equilibrium phases, but even these fractional DTCs, which we didn't expect at all, to be very honest. And then I showed you that instead of doing hard quantum calculations, for most practical purposes, you can actually study similar physics in classical phases. There are quantum features, if you want to really look at certain eigenstate order features that you can't get classically, but as long as it's something that you can diagnose with some simple, local observables, almost all the time you can also study that classically. And then in the final part, I didn't have much time, but I just flashed this, and maybe if you're interested, we can also generalize this to systems which have no time translational symmetry, but nevertheless you have correlations in time, and that allow you to still see prethermalization and see interesting physics, and we find new universal scaling regimes for the time scales over which you can observe these. So then let me oh yeah, and you can ask, there are many open questions to ask. One of them is, for example, can you have topological phases without time translation symmetry? And the answer is probably yes. So then one of the last things I really want to do is to thank you for listening, and also my collaborators. So these are most of the work I've shown you is really due to these two really amazing PhD students. So Hongjing Zhao, he just graduated. He was a student of mine in Imperial, and he did all the work on the random multipolar driving in the end. And the first part on these higher order and fractional time crystals is really, the credit goes to Andrea Pizzi, who's a PhD student in Cambridge, and who in the first lockdown happened to visit me in Munich. And then instead of staying for 2 weeks, he ended up staying for over a year. And we had a really productive time, albeit, all the difficulties of the lockdown. And then let me also thank these other people here, especially, Joe Wofrosch. I've shown some work of him here, and then Andreas Nummenkamp, my old supervisor Roderick Messner, Florian Mintert, and also Takashi Mori, with whom we have all collaborated. And with this, let me thank you, and yeah, please, happy to answer any questions.
Thank you, Johannes, for this excellent and very interesting talk. Let us thank Johannes. And we have time for questions, so please go ahead. Perhaps until Rio.
Yes. So yeah. So maybe this is a generic question, but like, what the term? So prethermal phase happens because it stops observing. It is very rare to observe, and so then what determines the temperature of that state?
Yeah, very good question. It's the initial state.
Yeah. So it's okay.
Yeah. So so this is why classically, it's the same classically in our classical prethermalization. So what we do is we always, you can think of starting in a polarized state in, let's say, the Z direction. And then if you would do the classical time evolution, nothing would happen since they're all exactly parallel. So what you have to do is you give basically each a random spin in like a random azimuthal angle in a different direction. And then you can calculate just for that initial state with a random angle for each spin, you can calculate the expectation or the energy of the Hamiltonian, and that basically will set the energy density of the prethermal state. So we have actually done that we looked at the stroboscopic value of the polarization, for example, in the 4DTC, measure Z direction every 4 periods, and then plot the value as a function of this initial spread. And it actually looks just like an order parameter where the axis would be temperature.
Mm-hmm.
And one question, for example, what is the critical behavior and so on? So it seems to be that, the initial state energy density maps almost 1-to-1 to the temperature of the prethermal state.
Am I right, though, that the temperature will increase as time evolves? Like at the end of the prethermal state, it starts to increase the temperature? I mean, because I think at the end of the day...
Well, at the end of the day, you basically heat out of the prethermal state, yes. But the idea is that as long as you're in this prethermal regime, there is actually a state which is described by essentially a thermal ensemble for a fixed temperature. Yeah.
Right. So I was trying to ask, like, because you start with this long time scale that is determined with the temperature that's determined by the initial state, and then but at the very end, presumably the temperature increases and it will cross the critical temperature. And will you see any like critical behavior there? Is kind of the naive question.
Oh yes, that's a very good question. So I think that in a strict sense, you should only think about it a temperature in this regime which is stable. I think as soon as you basically go out of the regime where you deviate from that plateau, then it's probably more a proper non-equilibrium system where there is no well-defined.
Because it starts to observe, and so probably it's really non-equilibrium.
Yeah. But nevertheless, the question of whether you can, for example, look at length scales and how they diverge towards the, that's still a valid question. Yeah. So there might still be some remnants of critical behavior observed.
Yeah. Thank you.
Yeah, it's a good question. Yeah.
Do we have any further questions from the audience? Sergey, please go ahead.
Yeah, can you maybe explain again what makes the classical analogy working when you actually started from the quantum system? So what do you have to cook up in the quantum system so that the classical comparison or analogy will work?
Yes, so I think you can basically ask the question, what stabilizes all this this physics, and I think that it's really the simple basic intuition of how you basically lose an ordered state. Yeah, because you can essentially, the time dependence in between these kicks and so on. That's the micro motion which gives you basically time thermalization symmetry breaking. But if you think stroboscopically, a 2DTC, just think every 2 periods is just some ordered state. Yeah. And so then you can just think of how you lose an ordered state. And this is by excitations, domain walls, by domain wall proliferation, for example, and simple, if you think of some simple easing system. And that doesn't require any quantum mechanics. This is really basically just energy arguments, local energy arguments, and so on. And in that sense, the reason why I think people for so long only studied quantum systems is more that it's a formalism issue, that you can basically have Floquet theory and an inverse frequency Magnus expansion. All this is just extremely natural in a quantum setting, but it's not very natural in a classical setting. And that's why thermalization in classical system came 100 years earlier than thermalization in the quantum system. Here it's the other way around, that pre-thermalization came earlier in quantum system and then later in classical system. But I think it's more coincidence. Yeah? And then once you basically understand that you can have classical pre-thermalization and you really think like, wait a second, what is the time crystal of the simplest cases all about, then you basically understand that you just need to try it. Yeah. So I'm just saying that it was surprising for us as well. Yeah. So that people hadn't at all thought about this and tried that. But the short answer is it's really just that the mismatch between local energy scales that would heat the system up and the large energy scale of the drive.
Would you call the FPU the dynamics also a pre-thermalization dynamics? Would you go as far as claiming that?
The FPU, what is FPU?
Fermi-Pastor-Ulam.
Oh, whoa, that's a good question. Short answer, I don't know. I would have to.
Okay.
But yeah, but it's a good question. Yeah. Yeah.
I don't know by myself. I'm just curious whether you. Okay, we can maybe discuss later.
Yeah.
One last question about the decorrelators, which you showed on some of the previous slides, from which you were also measuring the exponential growth.
Yeah.
The Lyapunov exponent. Did you also try or consider to compute the entire Lyapunov spectrum for these classical systems which you were studying, or is it of any meaning? Does it give? Can we expect anything interesting out of that, or which is something which you usually cannot do in quantum systems again?
Yes. Yeah. No, we haven't thought about this at all. No. Yeah.
But you could, right? In principle, should be possible.
I think so. So spectrum meaning that you really want to trace that and then do the proper Fourier transform and look at all the frequency components of that?
Oh, I mean computing all the Lyapunov exponents, not just the largest one.
Oh, okay. Yes, I think Yeah, it should be possible. Yeah. No, we haven't. What additional information would you expect from that? Or
that was my question to you.
yeah, no, we haven't thought about this, but it might be. Yeah, might be a good idea. Yeah. So here we just really wanted, when we did this comparison between the full quantum calculation and the classical, we just realized that everything is the same, scaling, blah blah. It looks really, you wouldn't tell the difference, except that we don't have anything for information spreading like entanglement entropy, and that's basically when we just thought a bit and then cooked up this decorrelator. But I think it's a very general thing. So yeah, I mean, we haven't thought about doing something more useful with it than comparing it to the quantum entanglement. Yeah.
Okay, thank you.
So can you can I ask? Yeah, so can you make the classical versus quantum analogs sharper by looking at the Fokker-Planck equation? Because Fokker-Planck equation is like, if the probability P is, if you view that as the wave function, then that Hamilton, the operator for the Fokker-Planck equation evolution can be looked at as a Hamiltonian. So I was just wondering if that analog might be useful or not.
So I'm not sure, because if you start with Fokker-Planck equation, I mean, this is usually dissipative physics, isn't it? I mean, if you
but there will be like so there's only drift term, and so if like formally you can consider Fokker-Planck. I mean, I'm not saying that it might be useful or not, but like the only thing that so you can make, how does it, like, I mean, you can consider probability distribution if you want to for deterministic dynamics too. It's just that the diffusion term is gone away, right? So it's just more or less formal maybe, but
yeah. So I think it's a very good question to ask how you would do that. So the one work exists where people do something analytically is the one by Takashi Mori, and what they essentially do is they take just spin systems and they do a semi-classical large S limit. So they essentially use the quantum formalism, inverse frequency expansions, and just shows that everything that you derive in terms of prethermalization bounds for that survives the large S limit. So that's one way. Whether there is for more general systems an alternative way of phrasing that or taking this this limit, that's a good question. Yeah, I don't know, because also the work by Polkovnikos is essentially just a numerical observation. Yeah.
Thank you.
We have a question also from Dario.
Yeah, is a simple question. I mean, you showed us that essentially all the relevant physics was already in the classical setup. I mean, you didn't need any quantum, but you also said that there are few features that are genuinely quantum. So what are them? I mean, I missed what are the...
Yeah. So the first thing is, of course, this one feature, which is absolute stability, that you can, discuss a lot about, whether, whether, for example, some time crystal behavior would persist forever or only be a transient that exists to astronomically large timescales. So far, we know that only with MBL, you would have this basically absolute stability forever. So that's the first thing that you wouldn't get classically. I mean, there are other ways of basically, if you have integrability or things like that, you might still also get it forever, but then it's fine-tuned and it's not properly robust in the sense. There are other things which are more subtle, namely you can have things like eigenstate order or, topological properties on the level of individual eigenstates. And that's also something that you wouldn't have. So that's why I said, if it's like some non-equilibrium behavior that you can measure by some local observable, like think of our local spin direction, I'm pretty confident that you can get it classically. But you could also have something which is more, which really relies on coherence of individual eigenstates. So you can basically now that you know basically what is classical, you can go back and try to engineer genuine quantum things.
Yeah,
that's possible.
And we have also questions or comments by Alexei. Please go ahead.
A very naive question, probably along what Ro was asking. So this long-range model, the quantum model that you looked at, where you used the all-to-all limit that was solvable and then did an expansion around, if I understood correctly. Would it make sense to look at the SUM limit, so promote spins from SU2 to larger SU group, and eventually go to the M to infinity limit where things might be solvable?
Yes, I think that is a very good idea, and in fact, I believe Andrea, he is currently not for this model, not for the time crystals, but in a slightly different context. He's currently playing with two coupled SUN spins, and then taking two spins in the classical limit, which we know are already chaotic, and trying to see how you actually take that larger. Yes, I think that's a good way to go. Yeah.
Okay, and another question is also probably naive. So again, you use long-range interactions because that's what you need to stabilize the order.
Yes.
Would long-range correlations help?
Long-range correlations. I mean, naively, I don't think so. No, because I mean, I can have. Let me think. No, long-range correlation. I mean, how do you? Yeah, I mean, okay. If you have long-range correlations, they would help. Yes, they do. Because they, you can think of some of the Ising model. Yeah. So the point is, the Ising transition with short-range interaction, you don't get it, but you also never get long-range correlations. So if you somehow manage to engineer something that has long-range correlations, I think even power law correlations would.
Well, I mean, I think, well, I don't know. I still don't have an intuition if it works, but I'm sure you know. I mean, what I have in mind, you definitely know. I mean, try to impose something like spin-ice rules.
Oh, now I understand.
Yeah. By correlations, because then you get you get to the degenerate ground state, but the correlations there are power law. Well, maybe you have to go to higher dimensions, but probably you can also engineer it in 1D.
Yeah. Good idea. Yeah. I mean, we were thinking, we haven't done that, but we were thinking on a related line, just take the 2D XY model, yeah. Look at like KT physics and stuff like this, yeah. So there we also know that we have the whole critical phase, and I would almost be, just so far, this analogy with initial energy density and temperature has worked so well that I think whenever you have some rigidity in the system at a given temperature, I think you would be able to see something like this. Yeah. As I said, it's surprisingly basic and surprisingly new that I think one can think of many examples. Yeah.
Okay, thanks.
Okay, do we have any other questions or comments from the audience?
Oh, am I still there? Yes.
Yes.
I thought, I stopped the sharing. I thought I hit the wrong button. Okay, but no, I'm still there.
It's okay. So it seems we are also out of questions. So in this case, let us thank Johannes again.
Yeah, thanks a lot for having me. Thanks for the questions.